Alright, doing this problem called construct binary tree from preorder and inorder traversal. Given two integer arrays, preorder and inorder, where preorder is the preorder traversal of the binary tree and inorder is the inorder traversal of the same tree, construct and return the binary tree. Okay, here this is the tree, this is the preorder, inorder, and output. Okay, let's maybe use a whiteboard. So the example tree that is given to us, let's say the same example tree. The example tree is 3, 9, 20, 15, and 7. Okay, first let's talk about what is pre-order and in-order traversal, right? So in pre-order traversal, you essentially first check the root, then you check the entire left subtree, then you check the entire right subtree. And in-order traversal, first you check the left subtree, then the root, and then the right subtree. Okay, so what would be the pre-order traversal then for this tree? So this tree, the pre-order traversal would be 3, right? And then left, and then you right again, you do first root, and then left, and then right. And here, in-order traversal would be you go to 9, then you go to 3, then 15, 20, and 7. Okay, so now the question becomes, hey, you are given this pre-order and in-order. How do you construct the tree? Okay, so what can we tell given this pre-order in order? What we can tell is the pre-order always starts in the root of the tree, right? So that tells us that hey, the root of the tree is 3, like that is undeniable, right? So this is going to be the root of the tree. And in order says left, root, right. So if I find 3 in this in order, which it's here, that means everything to the left of this will be on the left subtree of 3, and everything to the right will be in the right subtree of 3. Okay, so based on that, I know that 3 is a root, and I find this 3 in the in order array, and I see if there is something to the left, and there is something to the left. So I go this, and then the next guy again from the pre-order root left right. That means now again I'm on the left, but on the left the first guy will be the root again. So now 9 is the root, right? So I make 9 as a root, and I find this 9 in my pre-order, in my in-order, but I had already put a boundary here. Everything to the left of 3 is in the right, so 3, and I get this 9, and I see okay, there is nothing more in the left and the right of this remaining thing, so I'm done. And then I move to the right subtree, which is, and the right subtree boundary is this. This is my right subtree because on the right of 3. So in the right subtree, now we move further in the in order, in the pre-order, sorry. So 20. So 20, I find where is the 20 is, and 20 is here. So are there elements to the left of 20? Yes. So there, that means it has a left child. How many elements are there? 1. And which is this? Is this the next guy? 15. And 15 does not have anything in the left and the right. So I'm going to go 20's right child, and 20's right child is 7. So we're getting some sense of it. Let's take a bigger tree maybe to uh, get the idea more clear. So let's take like I don't know, 1, 2, 3, 4, 5, 6, 7. Let's make it 8. Let's make it 9. Some rather interesting. Like let's say this is the tree, right? So let's quickly write its pre-order and in order. So pre-order and in order. So pre-order would be 1, and then 2, and then 4, 5, 8, and then 3, 6, 9, 7, 10, 11. Let's write the in order. In order would be left. So 4, 2, and then what? 8, 5. Correct? 4, 2, 8, 5. 1 and then 963. Is it 963? No. Let me. Right. So left root and then right. So 4, 2, and then left root. So 8, 5, and then 1, which is correct. And then left. So left subtree is, so after 1, 3's left child is 6. So it will be 069, right? So basically 6 and then 9 and then 3 and then, so 7's left child is 10. So yeah, and left root right. So left 10's left is nothing. So 10 and then 11 and then 7. Let's quickly verify if it's correct. So 4 left root right. So 4 2 8 5 1 6 9 3 and left root right 10 11 7. Yeah, okay. And pre-order is 1 2 4 5 8 3 6 9 7 and 11. Pre-order is easier. So now, given this, how can we build the tree, right? So obviously we know that pre-order, whatever is the root, whatever is the first guy has to be the root of the tree. So that means 1 is the root of the tree. I find 1 here, so this is 1 here. That means everything to the left is the in the left subtree. So this is a left sub. This all of these have to be in the left subtree, right? So once left child, I go 2. I find it 2 here. So everything to the left of 2 is in its left subtree. So 4, and then everything in the right. So this 8 and 5. First you get 5, so you go 5, and 5's left will be 8, right? And then now you reach 1, so nothing is left. So this is your left subtree. Now you go 1's right subtree, and this is the 1's right subtree. In the 1's right subtree, first guy you see is 8. So you put 8 here. Oh, 8 is, sorry, 8 has already happened, not 8, 3. So first guy you find is 3. You find where the 3 is, so 3 is here. So you divide this 3. So this is left child, this is the left subtree of 3, this is the right subtree of 3. So let's go to 3's left. First you get 6, so you put 6 and you find 6 here. 6 right would be 9. Now you go to 3's right child, 10, 11 and 7, 3's right child. First you get 7, so it has to be 7 and you find 7 here. That means both of them are in the left child of 7. So left. First you get 10, so 10 and it's in the right, so it's 11, right? Is it matching? It is. So we get the general idea. The general idea is, okay, the general idea is what? General idea is the root or the current index in the pre. So basically you're processing pre-order array one by one by one by one, and what the relationships are gets decided by the in order array, right? So you find whatever the item you find its location in the in order array, and you create then the artificial boundaries for the left child and the right child, right? So let's come to the code to see if we can construct logic based on this. So what we're saying is that we have to return the tree, right? So the in order array, we are always keeping boundaries. So let's create those boundaries. So let's do this. I'll do return build a tree pre-order in order, and the we create boundaries in order array, which is from 0 to in order dot length -1, and we'll also have a index in the pre-order, which is 0. So this is what I am trying to do. Um, let's say I have int build tree, and I have this pre-order and in order. But aside from them, I also maintain like uh, a left boundary, or like a, yeah, left and right. So int left, int right, and I also maintain an index in the pre-order array. So the first thing that I have to do is if my pre-order index, if it's equals to, if I've reached the end of my pre-order array, right, then I can just return null. This would also be the case when your pre-order array is empty, right? Otherwise, what you want to do is you build a tree. So tree node, you call it root equals to new tree node with the value in the pre-order array. So pre-order of tree, and then you want to call left child and right child. So root, sorry about that, root dot left will be uh, build a tree, and but to be able to call that, you need to know where this guy occurs in the in order array. So maybe let's do a search. So if we do a search, um, equals to left I is less than equals to right I plus plus. If, and what if you don't find it? Is it possible that you don't find it at all? So avoid that case as well. So you do this, or if your left is greater than right. Yeah. So now that means there is a left and right. That means there is a window, and in that window you have to find this guy. Okay. So if in order of I equals to root dot well, let's call this define something, root index in order. Yeah. Let's call it -1, and once you find it, you call it I and break. And now what's going to happen with this is your root dot left will be pre-order in order. The boundaries for left will change. The boundaries for, so left boundary will remain the same. Right boundary will be root index in order -1, right? Left subtree would be on the left of this. So this is this, and once you exhaust left and right, which is where this condition will help, I guess. So, and pre plus one, you're always processing one guy next, and then root dot right equals to, again, okay, there's a problem. This pre plus one, this pre has to keep incrementing, and not the pre. You don't have to call the pre plus one. You have to call the index which is after all the traversals. Maybe make pre as a global. Uh, so maybe we keep here. Don't pass it. It will keep on incrementing. So we can maybe just increment pre here. Yeah. And so for the right, the boundaries will change as, for the right subtree, the boundary will be wherever root occurs here, +1 and right. Okay. So this, let's have a look at it. So we're building the tree. We're passing the boundaries in the in order array, which will contain the tree. Initially, that boundary is the entire array, and then we check. This is the base case where we have to return null. Otherwise, you just take the next element at this from the pre-order array, build it, create a node from this, and you check where that elements exist in the boundary of the in-order array, right? And you find that, and once you find that, on the left of it is where all the left subtree will happen, and on the right of it is where all the right subtree will happen, and so we call that recursively. All right, let's run and fix some issues. So line number 20, in order dot length. Okay, run again. Fix more issues. So pre-order, in order, int cannot be converted to tree node. I think this int is the problem. So you call it tree node, and I'll be returning the root. At the end, we have to also return root. Let's run. Okay, seems to work. So what we're doing here, I feel this is a little bit problematic in the sense that every time we are doing a search for an element uh, within the in order array. So for every guy, so for all n elements, I am searching it. Yes, the window is decreasing, but still, this search, can we do it once and save it in a hash map or something and then avoid searching again? Maybe, right? So let's do that as well. So let's say we do uh, hash map all integer uh, map, and we can create a map here. So we do a pass once. So for int I equals to 0, or rather for each, yeah, for int I equals to 0, I less than length, I plus plus. Okay, map equals to new hash map, and what you're gonna do is you map dot put, but that will only work if your array has a unique values, and it does have that, so that's fine. So map dot put, what's the key? What's the key? Key would be in order of I, and the value would be I. So you put this. So by doing this, now you don't have to search, right? You can just do map dot get root dot well instead. So that will avoid those searches. Let's run again and submit, and it works. All right.